Let's keep on rolling with the trig subs here. So this one doesn't look like what you might think of as a trig sub. I've got this 8x squared over 64 plus x squared squared. Now, if I'm looking for trig subs, I'm usually looking for something with square roots. But I don't have something with square roots. In fact, I have no square roots to be found. So why is this a trig sub? Well, it's a trig sub because we can still use the same basic principles. And one of the reasons that you know it's not a good candidate for some other methods, though there might be a method that we would learn later that could be useful here, is that the power inside this parentheses matches that power. Now, if this had been like 8x over this, I would recommend a standard U sub and you'd be done. But we don't have that. We have this matching power. And even if those powers were like a little offset, you might sometimes can kind of finagle your way through it. But in this particular case, because the powers aren't offset or anything like that, you've got to go with trig sub here. Or at least it's a good idea. So how do I make a trig sub? Well, because I don't have a square root, you kind of do. What you have to do is be a little more clever about it. What we can do is we can rewrite this. As square root of 64 plus x squared to the fourth. And the reason that works is because this is sort of like a 1/2 power, and 1/2 to the fourth, or 1/2 times a fourth, is 2. So instead of doing a 2, you're doing something to the 1/2 to the fourth. And so that ends up how it works out. This allows us to put it in standard trig sub form. So if I, instead of writing 64 here, I have an 8 squared there, I can then say, okay, well that looks a lot like this piece. Right, so that makes A equal to 8, and then that's my associated triangle with theta here. So then I can look over here and say, okay, x is 8 tangent theta, dx is 8 secant squared theta d theta, and then the square root of 64 plus x squared is 8 secant theta. So then at this point we can just plug in with everything we have. We can say, okay, that is 8, and x is 8 tangent theta, so that is 8 tangent theta squared. And then this is 8 secant theta, so I have 8 secant theta to the fourth. And then dx here is 8 secant squared theta d theta. So thankfully all of these 8s disappear, right? Because I have 8 times 8 times 8 times 8. So that's 4. And then I have 8 to the fourth, so that all goes away. So this reduces to tangent squared theta secant squared theta, or secant to the fourth theta d theta. Well, alright then. So when we do that, there's a couple ways to do this. The way that I think probably makes the most sense to do this is to turn everything into sines and cosines. Because if you turn everything into sines and cosines, you get sine squared theta over cosine squared theta times 1 over cosine squared theta all over 1 over cosine to the fourth theta d theta. So I have a cosine squared and a cosine squared. So that's cosine to the fourth over 1 over cosine to the fourth. That rewrites as sine squared theta d theta. So it all just washes out and you get sine squared theta d theta. Now what we have to do with this is we have to use the power reduction formula. So we end up with 1 minus, or 1/2. 1 minus cosine 2 theta d theta. So if we antiderive 1, that's just theta. So we have theta. And if we antiderive cosine of 2 theta, we get sine of 2 theta plus c. So we have 1/2 theta minus 1/4 sine of 2 theta plus c. Now we have to make a couple of choices here. The first thing you need to remember, and this comes up a decent amount, so this is probably a good identity to remember. Sine of 2 theta is 2 times sine theta times cosine theta. So using that, we can rewrite this as 1/2 theta minus 1/2 sine theta cosine theta plus c. Now the next thing you have to think about is, all right, I have a theta. I don't have a sine theta. I don't have a cosine of theta. I just have a theta. So how do I get that? How do I get theta? Well, I get it from here. I can say x over 8 is tangent theta. So then if I take the inverse tangent of both sides, I get 1/2. So I take the inverse tangent and I get inverse tangent of x over 8. So I need sine of theta. Well, to do that, I'm going to look at my triangle. That's x over this square root. So that's x square root 64 plus x squared. And I need cosine of theta. Well, that's 8 over that square root. Don't forget your plus c. Don't forget your plus c. So now I have 1/2 arctangent x over 8. So those cancel. The 1/2 and the 8's cancel. So I have 8x over 2. So that's 4x over 64 plus x squared, because those square roots cancel each other, plus c. Lo and behold, I did it correctly. My cheat sheet does in fact tell me that I've done this correctly. Honestly, I'm going to tell you, I thought maybe I made a mistake. So what this shows you is that, needing to understand several different things along the way, specifically right now the regular trig integrals, without them you're going to have a hard time doing these trig substitutions, because you're going to end up needing the techniques you learned in trig integrals to solve trig subs a lot of the time.